these are examples of cyclic groups. Okay, so we're gonna try. So you please consider the integers with sum, or consider this subset of the integers. It's the multiples of 3. This is the notation for multiples of 3. So you get -3, 0, 3, 6, -6, all those. Okay. So we can see that the multiples of 3 with the sum is a subgroup of the regular integers. Okay. And in particular, you know, we usually use this notation: 1 plus 1 plus 1 plus 1 plus 1 n times will generate the m. And with the notation of the book, this means this 1 to the n means iterate 1 with 1 composition, right? The operation n times. Okay. So in this case, the operation is the regular sum. Okay. So that's what this is the favorite example for cyclic, because turns out the integers are generated but only one element. So this notation means the smallest subgroup containing better like this, the subgroup generated by this element 1. Okay. And turns out that this one generates all the group. Okay. So I could do also this the set of generating all the multiples of 3. So this is like this. Okay. So this is in other words, this is the smallest group containing that number 3. Okay. So that's what we're gonna to work today. So this notation, so definition, let's say definition, means all is that the k iterations A for k is an integer. Okay. So that means this means A compose A compose A compose A k times. Again, when I have the integers, the composing is plus. Okay. So let's give another example. I mean, I try to give you as many examples as possible. So, example. If h equals 2 to the n with n is the integers, then h is a subgroup of the multiplicative group of non-zero rational numbers Q star. Okay. So Q star is with multiplication. So are the rational numbers except the 0? This is basically Q minus the 0. Okay. So if A belongs equals to let's see. So we're claiming H is a subgroup of the multiplicative group of non-zero rational numbers like this. So we're gonna show that H is a subgroup of this. Okay, so let's clarify that. Something is wrong with my eraser. Let's show H is a subgroup of Q star with multiplication. So remember we have a proposition that it says somebody's gonna present a proposition. We learn the proposition saying that if okay. That H is subgroup of G, so let's put it like this. Recall H is a subgroup. H is a subgroup of G if and only if H is different than empty set and whenever G and H belongs to H, then G H inverse belongs to H. Okay. So to show that H is a subgroup of Q star, right? So we need to consider let G and H belongs to G. G and small h belongs to the set capital H. Okay. So what is capital H means is equals an element is capital H if the element is equals to 2 to the n for some integer n. So let G and H belongs to H, then there exist m and n integers such that G equals 2 to the m and H equals 2 to the n. So we need to show that we need to show by proposition. This is a proposition, no? This proposition from the book is proposition 3.31. And one of you is going to present this proposition. We need to show that G times H inverse belongs to H. Okay. So what if H equals 2 to the n, what is H inverse? So we know because this is rational numbers, it has to be 2 to the minus n, right? All right. since h times h inverse equals 2 to the n times 2 to the minus n is 2 to the n minus n, and this is 2 to the 0, this is the identity. Okay. So if h equals 2 to the n, what is h inverse? Answer. H inverse is 2 to the minus n, because this, okay, so if we consider g times h inverse, we have g, no, g, 2 to the m, oh, no, 2 to the m, 2 to the m, times h inverse, that is 2 to the minus n, and this is 2 to the n minus n. And since n minus n is an integer, then two to the minus n minus n equals or belongs to h, right? Because any element of h is of the form 2 to the n when n is an integer. So therefore, since 2 to the n minus n belongs to h, so g times h inverse belongs to h, as we wanted. Therefore, h is a subgroup of this group, right? And what we can say is that further, the group H is the group generated by 2. Okay? Because it's all the powers, by our definition, are all the powers that belongs to the integers. Okay, so that's a very nice example. So now we're gonna do the proof. We're gonna do a proof, and then some more examples, and then I will recall some of the propositions were assigned. So this is a theorem. Let G be a group and A be any element in G. Then the set is a subgroup of G furthermore A is the smallest subgroup of G that contains A. Okay. So that's really important. Okay. So that gives us a lot of intuition to create subgroups. Okay, it's like I showed you before, when I was showing you examples of subgroups. So these are subgroups of the quaternions, non-trivial. These were subgroups of the Klein group. These were subgroups. This guy, this guy, this guy, this guy, this guy. Oh, with this one, no. These are non-proper subgroups, non-trivial subgroups of C12, non-trivial subgroups of C6, non-trivial subgroups of the C to the Pn. Okay, non-trivial subgroups of the integrals module A, a non-trivial subgroup of C module 4. Okay, so the so you see, now you see how I was able to make all the subgroups because I knew this theorem in advance. Okay, so let's prove this. So proof. So we will use which one we want to use. Let's use, yeah, just to change. Yeah, so I think either way, but let's use proposition theory. We'll use the proposition theory. Set a subset, and somebody is gonna prove that too. Subset H of G is a subgroup if and only if it satisfies the following conditions. Oh, yeah. So it must satisfy number one. The identity belongs to H. 2, if H1, H2 belongs to H, then H1 product of the operation is in H. So the product of the elements are in H. Product, by product I mean the operation, no? So let's put the circle, that funny circle. And whatever group it is, any operation that make it a group. If H belongs to N, then H inverse belongs to H. So let's prove that's a group using this, but this is gonna be similar to the one we just did, right? Or here. So so since E belongs to H, right? So we need to prove one. Since N belongs to the integers, 0. Since 0 belongs to the integers, A to the 0 is equal to the identity, right? So therefore, the identity belongs to H. The next one says if H1, H2 belongs to H, then H1 operation. So if H1 and H2 belongs to this guy, then H1 equals AK, H2 equals to some AM for some integers K and M, right? Therefore, H1 operation H2 equals AK operation AM, and by properties, by the definition of this operator, right? This is equals AK plus M, okay? Because that's true for any operation, okay? And since K plus M belongs to the integers, then AKM belongs to H, so the operation H1, H2 belongs to H. Okay. Now for the inverse, choose, as we know, we choose A, if choose H belongs to H, so H equals to, so let's choose an element, any element of H. This is A to the N, right? So if we choose A to the minus N, then we got A to the N, no, but like H compose A to the N minus N equals AN to the N minus N. This is AN minus N. This is A to the 0, and this is the identity. So this belongs to H, right? So therefore, H times minus N gives you, sorry, no, equal. I don't know why did I do that. Equal, right? Well, I mean, obviously we know that this already on H. I will not need to say that because it's confusing. I need to show that this guy equals E, and I need to show the other way. I need to show A minus N compose H. This A minus N compose A to the N, E to the 0, and this is E. Therefore, so by definition of the inverse, A to the minus N equal H inverse. And A to the minus N belongs to H. Because any element of H is of the form more than H. H is A, no? So that's why I'm proving that it's a subgroup, right? So, okay, here. Okay, so that's the end of the first part. So that's a subgroup, and clearly any subgroup H of G containing A must contain all the powers of A by closure. Okay. Therefore, A is the smallest subgroup of G containing A. So this by closure means if you contains A, then you must contain A compose A, and then you must contain A compose A compose A. So you know you have to, by closure, you compose A by itself as many times, and that must be part of the subgroup, because that's the definition of a subgroup. You operate an element with any other element, and it must be inside of the subgroup. Okay. So now let me see, make sure this is recording. My battery is going low. Yeah, I think it's good. So we call those some remarks. We call A the cyclic subgroup generated by A. Okay. We said if the G contains A such that A generate all the group G, then G is a cyclic group. Okay. And A is called the generator. Okay. Generator of G. All that terminology is important for us to be able to communicate. So let's give a definition, because this definition is going to be important. Definition of order. Okay. We define the order of A to be the smallest positive integer n such that A to the n equals E. And we write order of A equals n. Okay. If there is not such n, we write the order of A equals infinity to denote the order of A. Okay, so this is for example. Let's give an example just to consider C6. Okay, so we already said that C6 is generated by the relative primes. So it could be 1, it could be 5, and that's it. So C6 is a cyclic group. So we did it in one of the previous videos. So we also 2 plus 2 plus 2 equals 6, and this is 0, right? This is the E of this subgroup. So the order of 2 is 3. Okay. And the subgroup generated by 2, we already did this, is 2, 4, and 0. Okay. So what is the order of 5? The order of 5 is 6, right? Because it has to be 5 plus 5 plus 5 plus 5 plus 5, 6 times to give you the 1. Okay. Okay. So more examples, or better. The last example, and then we're ready to write the theorems and propositions that I assigned for presentations that soon are gonna be available. So theorem. The group of units U9 in C9 is a cyclic group as a set U9 is, so what is U9? Is 1, 2, 4, 5, 7, and 8. Are the relative primes to 9. So 1, 2, 4, 5, 7, 8. Okay. So basically 3, 6, and 9 are not there, right? The element 2 is a generator for U9. Since 2 to the 1 equals 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 10, module 9 is 1, 2 to the 5, what? 2 to the, no, sorry, 2 to the 4 is 16, module 9 is 7, right? 7, sorry. 2 to the 5th is 32, module 9 is 3 times 5, right? and 2 to the 6 is 64. Module 9 is 7 times 9 is 63, so module 1. So you see the order of 2 is 6 in U9. Okay. Okay, so we're ready for the important theorems. So those are very good for intuition. Make sure it's recording. Yeah, okay. So it goes like this. Theorem, first theorem. Every cyclic group is abelian. So that means commutative. Okay, so that's did I send that one? Probably not because it's too short. So let G and H belongs to the cyclic group. So something. So like this, but if it's cyclic, it has a generator, no? So let's say it's like this. So G equals A to the M, H equals A to the N, and G compose H is AN, compose AN, and this is AN plus N. But this is, you can write it like AN plus AN, and you can write it like AN compose AM, and this is just H compose G. Okay, so it's abelian. So this is, that's right. Okay. So you see, that's what people love, these cyclic groups. So now we do subgroups of cyclic groups. Subgroups of cyclic groups. So theorem, and somebody has to present about this. This is every subgroup of a cyclic group is cyclic. Every subgroup of a cyclic group is cyclic. And then corollary. The subgroup of the integers. Subgroup of the integers. Let me connect it. Last time I connected, it didn't record the sound. The subgroup of C are cyclic Oh, sorry. The subgroups of C. Oh no. Okay, sorry. The subgroups of C are exactly let's see, are exactly NC for n equals 0, 1, 2, and so on. Okay, so as I showed you on so many examples, so this the matrices, remember? So multiples. So the subgroups of C are multiples of 3, multiples of 2, multiples of 5, multiples of 7, etc. Now, proposition. So we're almost done. Maybe this video is too long, but I'll make sure I cover all this. Proposition. Let G be a cyclic group of order n and suppose that A is a generator for G. Then A to the K is the identity if and only if n divides K. Yeah, this is very important. Let G be a cyclic group. This is very important for your homework. If there is a problem, a proposition you need, is this one for your homework. Let G be a cyclic group of order n and suppose that A is a generator for G. Then AK is the identity if and only if n divides K. Okay. So sorry it was a little long, but I want to make sure I cover all these cyclic groups to give you enough material for the homework. Okay, thanks for